Hello everyone, and thank you for listening in today. My name is Soujanya Chatterjee, and today I'll be talking about our work on assessing the severity of pulmonary obstruction from respiration phase-based Wheeze-Sensing using mobile sensors. This work has been done at the Digital Health Lab, Samsung Research America. Obstructive pulmonary disease is a lung disorder characterized by narrowing of airways causing obstruction of airflow from the lungs. Some of the common conditions are COPD, asthma, pneumonia, and cystic fibrosis. The primary causes of OPDs are infectious respiratory viruses such as the novel coronavirus, SARS, MERS, cigarette smoking, and pollution. More than 15 million people in the USA are diagnosed with OPD, and more than 12 million of them remain undiagnosed. OPDs are the fourth leading cause of death in the USA. The ongoing coronavirus pandemic has caused the COVID-19 disease in more than 4 million people across 227 countries. More than 250,000 people have deceased, and unfortunately, the death toll is rising by the day. Some of the major symptoms of respiratory diseases are shortness of breath, chest tightness, cough, and wheezing. Diagnosis of these symptoms leads to the subsequent treatment and cure. State-of-the-art diagnosis include auscultation via stethoscope or diagnosis of lung function via spirometry, both of which usually require the presence of physicians or a visit to the hospital or the clinic. However, given the COVID-19 scenario, when the hospital staffs are overworked and the hospitals are overcrowded and all the social distancing measures are in place, wouldn't it be nice if the patients can do their own pulmonary assessment anytime, anywhere with the smartphones? Hence, our research question is the following. Can we develop a mobile sensor-based system as a convenient means of assessing the severity of pulmonary obstruction? Prior works on mobile-based pulmonary assessment have been done to estimate lung function from natural walk, cough sound, and forced exhalation sound. These methods are reliable, however, such activities pose a twofold challenge in terms of usability and require training. For instance, forced exhalation can be a risky maneuver for severe patients and usually require the support of a trained personnel. In our work, we develop a method that transforms the smartphone into a convenient tool which patients can just hold on their chest to assess their pulmonary condition via the sensing of the presence of symptomatic wheezing. Wheezing is one of the most important symptoms of pulmonary obstruction. It is caused due to rapid breathing through the narrowed lung airways. Wheezing may occur during inhalation or exhalation phase of the respiration cycle and is usually longer than 250 milliseconds. The severity of wheezing depends upon the location and extent of pulmonary obstruction. Obstruction in the upper airways and partial obstruction of airways results in low severity wheezes, while obstruction in the lower or central airways and acute obstruction usually results in high severity wheezing. To develop our work, first we conducted a study to collect data from 131 participants, which included 91 COPD and asthma patients and 40 healthy subjects. Participants used Samsung Galaxy Note 8 and Samsung smartwatch and wore Zephyr bar harness chest belt during the entire session of the study. We collected continuous sensor data from each participant for 20 minutes when the participants performed a set of tasks such as sit silent, supine silent, natural coughing, spontaneous speech, and reading. We also collected spirometry data to obtain the standard measures of lung function. We collected audio and accelerometer and gyroscope data from the smartphone. We also collected respiration data from the rib sensor of the chest belt. The next task is to annotate pulmonary symptoms from audio data. Annotation of 40 hours of data is challenging and intractable for a few experts and health researchers. Hence, we utilized crowdsourcing for this task. We recruited 12 random annotators for this task. We segmented the continuous sensor data into 1-minute chunks, and in the first phase, the annotators annotated the audio data just by listening to them. Expert reviews revealed that the annotation accuracy for cough was 72.2% and for wheezing was 35.5%. To improve the annotation accuracy in phase 2, we added spectrogram visualizations and updated the instructions for annotation. This improved the accuracy to 95.32% for cough and 46.15% for wheezing. To establish that the learning effect doesn't confound our finding, we employed a separate group of 4 annotators to perform listening and visualization based annotation with the updated instructions. Finally, we obtained annotation for occurrence and the severity of pulmonary events with an accuracy of 92.27% for cough and 86.38% for wheezing. We use these annotations as ground truth levels to develop our model. Next, we describe our MV system to detect the occurrence and severity of wheezing. The system takes in audio and breathing data as input. The first task is to segment the audio data based on the respiration cycles. When the phone is held against the chest, we detect the respiration cycles from the expansion and contraction of the chest using the smartphone accelerometer and gyroscope. And we detect the respiration cycle from the chest-mounted drip sensor when the phone is held at an arm's length. Next, we segment the audio data into 19,212 windows based on the inhale and exhale cycles. Since we are interested in detecting pulmonary symptomatic sounds, in the admission control stage, we remove those audio windows which contain silence and which contain speech. Finally, we are left with 8,491 windows which contains body sounds and is transmitted to the next stage. Next, we utilize the crowdsource annotations to level the body sound windows into the occurrence of wheeze versus non-wheeze, where the non-wheeze constitutes to be the cough, throat clearing, and normal breathing sounds. We also level the wheeze windows in terms of the severity levels as high and low severity wheeze. Next, to develop the wheeze detection model, first we perform time and frequency analysis. We observe that since wheezes are of musical and continuous nature, their presence demonstrates a typical continuous near horizontal lines in the frequency spectrogram. On the other hand, cough and throat clearing are discontinuous sounds characterized by short explosive bursts having relatively higher amplitudes. Using the insights and observations from the time and frequency analysis to differentiate between wheezing and other pulmonary sound, we extract 32 frame-level time and frequency domain features, and we use 11 statistical functions to obtain 352 aggregated window-level features. Next, we train various supervised classification models and validate them using leave one participant out cross-validation. We observe that with the top 30 features, gradient boosted tree based model can detect wheezing with a recall of 81.87 and an F1 of 87.96. A sample model output shows that this model can classify each respiration phase based audio windows into wheeze versus non-wheeze. The detection of wheezing leads us to the wheeze characterization module, where the goal is to characterize a wheezing sound as low versus high severe wheezing. We investigate the acoustic characteristics of low and high severity wheezing using the parse spectral density plots. We observe that the parse spectrum of high severity wheezes are concentrated towards the frequency band ranging from 1000 to 5000 Hz. And in contrast, the parse spectrum of low severity wheezes are mostly concentrated towards the lower frequency bands of 100 to 1000 Hz. Moreover, high severity wheezes usually have higher pitch and intensity as compared to the low severity wheezes. Using the insights from the above analysis, for each wheeze sound window, we compute the absolute and relative density from 6 different frequency ranges. In total, we compute 12 part spectral density features. We also compute 264 chroma and MFCC-based window level features to capture the difference between the intensity and pitch of high and low severity wheezes. In total, we compute 276 window level features. Next, we train various supervised classification models and validate them using leave one participant out cross-validation. We observe that with the top 25 features, gradient boosted tree-based model can characterize wheezing sound into high versus low severity levels with a recall of 74.62 and F1 of 79.47. The final output of the characterization module looks like the following, where the wheezing sounds are classified into low versus high severity levels. Next, we show how we can use the MWheeze system to assess severity of pulmonary obstruction. Standard spirometry test produces the following lung function measures. FVC measures the total volume of air expelled. FEV1 measures the total volume of air expelled in the first second of exhalation, and FEV1 by FVC measures the ratio. Usually, the ratio is used as a measure to estimate pulmonary obstruction. Our goal is to develop MWheeze-based objective wheeze measure to detect the severity of pulmonary obstruction and show the correlation with the standard measures. To develop the MWheeze metric, first we obtain respiration phase-based wheeze windows from the MWheeze system. Next, we observe that a user may experience three types of wheezing. First, wheezing may occur only during the inhalation phase, termed as inhalation-only wheeze. Second, wheezing may occur only during the exhalation phase, termed as exhalation-only wheezing. And third, wheezing may occur during both inhalation and exhalation phase of the respiration cycle. We term them as the respiratory cycle wheezes. Clinically, the presence of respiratory cycle wheezes indicates acute pulmonary obstruction. We leverage this insight to develop the following wheeze metric, which is the probability of occurrence of respiratory cycle wheezes as a proportion of respiration cycles containing respiratory cycle wheezes and the respiration cycles containing all the three types of wheezing. Interestingly, we observe that the metric shows statistically significant negative correlation with the FEV1-FVC ratio. That is, in our data, severe patients having lower FEV1-FVC ratio experienced higher likelihood of respiratory cycle wheezing. Hence, we propose that this metric developed from the MWheeze system demonstrates the feasibility of assessing pulmonary obstruction. In summary, in this work, we developed MWheeze, a smartphone-based method for assessing the severity of pulmonary obstruction via Wheeze-Sensing. It is important to note that our work is not to replace, but to complement the traditional methods of pulmonary assessment. Our Envision system is a significant step towards telehealth. We hope that our work will be of high impact in the post-pandemic world, where people can use such systems to monitor the respiratory symptoms remotely when in self-isolation. Our work has several limitations that present exciting opportunities for future research in the HCI and health community. First, in the future, mobile sensor-based methods can be developed for the passive sensing of relevant respiratory symptoms such as chest tightness, chronic cough, and shortness of breath. Second, our study was conducted in the controlled lab environment. In the wild studies may introduce several new challenges such as detecting symptoms in noisy environments. This would be of interest for future research. Third, longitudinal studies can be designed for developing models to forecast or predict pulmonary exacerbation under various contextual influences. And fourth, in the future, privacy-preserved methods can be developed for passive assessment of lung function from natural speech. Thank you very much for listening to this.